All right, I'm going to give you a little bit of a tutorial on chair structures, both drawing and doing some conformational analysis. I'll try to keep this brief, but just to give you guys some guidance as you're working further in this module. So I've drawn cyclohexane out. I've shown it with the bond line structure, and in bond line structures, you use dash and wedges to show orientation of groups or atoms. So there are wedges. Wedges are towards you, and there are dashes. These are away from you. And cyclohexane is all carbons and hydrogens. There's no other substituents on the ring, but we'll look at a derivative of cyclohexane in a moment. If you think about the bond line structure, it appears that the ring itself is planar. But we know that the carbons around the ring are sp3 hybridized. And so that means they're tetrahedral. And they want to have 109.5 degree bond angles if completely optimized. So this projection doesn't really show the true shape of cyclohexane. Now, what I want to note here is that for me, if I think about an axis here, if I were to flip that structure or lay that structure down on its face, let's say backwards, then the wedges, these are going to be up and the dashes will be down. Okay, and so moving along here, we're going to convert that cyclohexane bond line structure into a chair. So a chair is all about lines of parallel. So I'll start here with one chair. I like to draw, when I'm learning, two parallel lines like such. Let's draw another set of parallel lines. And then we'll connect the bonds, the ring, with a third set of parallel lines. So that is a chair structure. I'm going to number my chair just so you can follow things a little bit easier. I suggest doing this. If you look at carbon at the bond line structure, I've gone clockwise in my numbering, so I want to be consistent and go clockwise in my numbering for the chair as well. You can start number one wherever you want, but you want to be consistent and stay clockwise. So the easiest place for me right now is just to put one there. That's 2, carbon 3, 4, 5, and 6. All right, so I haven't shown the hydrogens yet, and typically you won't show hydrogens, but for this example I will, so you can see how they change their orientation in going from one chair structure, let's call this chair A, to chair eventually B. All right, so one thing I want to point out here is on the chair, we're going to highlight a few carbons here. So I have this carbon here and this carbon here. And so those represent the headrest and the leg rest of the chair. So headrest, leg rest. And they're good hallmarks or landmarks for your chair. Okay, so we want to go ahead and show the substituents on the chair. There are two things to note. We have, let's say, let me get rid of this here. We have axial and equatorial positions. So axial and equatorial. Axial, these are going to be straight up or straight down off of the chair. Equatorial bonds, these are upwards or downwards along the perimeter of the chair structure itself, but not straight up or straight down. All right, so if I go to carbon 1, if you look at the bonds that connect to form the carbon 1, or the carbons connected, it's in an upward direction. So there's an axial group straight up. At carbon 2, if the axial group has to be down then, so axial down. At carbon 1, if the axial is straight up, then the equatorial can't be upward. You can't have two bonds in the same general direction. And so equatorial bonds, they're going to be perpendicular to lines that make up the ring. And so if I draw in the equatorial here, and you look at this bond right here, let's highlight it a little bit. Let's redo that. Let's go ahead and make that a little smaller, highlight. If you look at this bond right here, it is parallel to that line and that line. So if you keep your equatorials parallel to the lines in the ring, then you'll draw your equatorial bonds correctly. Let's go to carbon 2. The down bond is axial and it's straight down. So the equatorial must be upward, but also parallel to some set of lines that make up the ring. So I'll highlight those again. We'll use green here just so you can see it clearly. That's in that direction. So those are parallel to those two lines. Okay, let's talk about the substituents. For cyclohexane, it's all hydrogens. Remember, if it's on a wedge in the bond line, it should be up than if you're tipping it backwards. And so the reds here are both on wedges. So I'm going to make the hydrogens that are red both up in the chair. So that's going to be axial up. And then here's equatorial up. The blues, they're going to be downward. And so here the down is equatorial at carbon 1. And then at carbon 2, the down is going to be axial. So let me get rid of this number here. It's in the way, and we'll renumber it in a moment. So down is a blue hydrogen, axial down. And you can see that axials are either straight up or straight down. And the direction will be noted or decided upon by, is the carbon it's attached to upward or downward in the staggered shape that it's in. So that was carbon 2 there. Okay, one other thing to note here, just so you guys get used to this, thinking about it this way, we're going to go ahead and just make a comment here. That's axial, that's up, as it should be. It came from a wedge. It's axial. This is down, and it's equatorial. So when you go to the next carbon, it alternates the pattern. If you see here, that's equatorial, but it's up. And this is axial down. So you can see that looking at carbon 1 and then carbon 2, if the axial is up on 1, then it must be down on 2. And so that pattern alternates all the way around the ring if you draw in all the groups. Okay, so what I want to do now is take that chair and draw a conformational isomer of it through a chair flip. And so I'm going to draw the chair a different way now. I just like to draw the parallel lines again. You don't have to do this, but it helps you get the shape of the chair at least relatively correct. So what was the headrest becomes the new leg rest. And so if I identify that, the new leg rest is right here. What was the leg rest becomes the new headrest. So there are your two landmarks to kind of help you get your numberings correct. The headrest was carbon 1, so now that's carbon 1. And I went clockwise, so it's 2, 3, there's 4, the new headrest, 5, and 6. And so now I can think about putting in my bonds at carbon 1 and 2. So carbon 1, we're going to have an upward position, equatorial, and a straight down axial. At carbon 2, the up is going to be axial now, and the equatorial will be downward. And so if we put in the hydrogens now, let's start with the red hydrogens from the last chair. The red hydrogens that were axial become equatorial. And so now at carbon 1, it's still up, but now it's equatorial and up. The blue hydrogen at carbon 1, it's got to stay down still. It was equatorial down, and so it is now axial and down. Up always stays up, down always stays down, but the equatorial axial patterns alternate when you go from one chair to another. Okay, like so. And then if we put in the hydrogens at carbon 2, let's start with the red. Carbon 2 has an equatorial up, but now it's axial up. And then the blue will be the down, which is now equatorial. And so if we just label that again, we're going to have here, down, and equatorial. And this will be up, still, and axial. So what you have here are conformational isomers for cyclohexane. Okay. Now, the two chair conformations, we'll call this second one chair B. So chair A and chair B, these are equal in energy. So chair A here and chair B are equal in energy, or they're equal in stability. And the reason why is, let's take a look. So I'll go down a little bit. I'm going to redraw these chairs a little bit differently. Oops, let's keep those colors the same. So I'm just going to focus on chair A for a moment. And I'm going to show you carbon 1, the axial hydrogen only. So we're going to do a little bit of conformational analysis looking at the axial groups. And so I'm also going to include the other axial hydrogens on the same face of the chair. And we're going to outline some interactions here. So if you look here, the carbon here that's attached to the red hydrogen and this carbon here, those are 3 carbons separating these 2 hydrogens here and here. If you go the other direction, there's another carbon with an axial group in the same direction. And there's 3 carbon atoms that separate these 2 groups as well. And so these groups are almost eclipsing each other in what we call 1,3 diaxial interactions. Okay, so if I want to look at the other chair structure, let's draw that out again. Oops, make sure we draw that conformation correctly. And I would number this. Let's go ahead and number these 2 chairs if that's carbon 1. And let's just focus again on 1 here again. And we're going to draw the axial substituent. I think it was a blue. And let's draw in the other axial substituents on the same face. So I've got 1 here and 1 here. And so once again, if we highlight the carbons where I've shown hydrogens, I got one here, here, and here, I'm showing the hydrogens that are relatively 1-3 positions from, oops, sorry. That are relatively 1-3 away from this hydrogen. So I'm going to circle those. Let's highlight those interactions again. So you've got 1-3 diaxial interactions. Again, and let's note what kind of interactions are taking place. So for chair A, once again, chair A here, chair B here, all the 1-3 diaxial interactions are between hydrogen, hydrogen. Over here, they're also between hydrogen and hydrogen. So both chair conformations have exactly the same 1-3 diaxial interactions, and so they're going to be having equal energies in that sense. And so I would say here that is basically the simplest explanation of why cyclohexane conformations are equal in energy. So if we think about equilibrium areal, let's go back up. We could draw those to be relatively the same distance, or they're in equilibrium with one another. Basically, they're 1-to-1. And so these are rotations about sigma bonds in a chair flip. And so chair flip implies a conformational change. So these are conformational isomers. Okay. Now, I'll do another example here. So let's do another example where we have something that's substituted on the ring. So let's draw cyclohexane. Again, instead of having all hydrogens attached, let's put on something that's not a hydrogen. And I'll just keep it on a wedge. Let's make it a CH3 group. Okay, if you want to draw in the hydrogen here, that's fine. All the other hydrogens, in fact, let's do this. Let's make those different colors. So I have a bond here, oops, and a bond here. We'll make one of them the red, CH3. And again, let's make the dash a hydrogen in this case, the blue. And so I'm going to draw out 2 chair structures again. Let's number this one more time. Let's just call that carbon 1, 2, 3, 4, 5, and 6. So I arbitrarily numbered it. I just put carbon 1 here because it was easy. And I am numbering it clockwise. So when I go and draw the chairs, again, I'm just going to start with cyclohexane and set it up properly. So there's 1 chair conformation. There's another. If we kind of notate where those headrest, leg rest, headrest. Now you can number your chair 1, 2, 3, 4, 5, 6, starting wherever you want. I think I'll just go ahead and call that carbon 1, and that's 2, 3, 4, 5, 6. I want to number the other chair consistently, so this better be carbon 1 because the headrest becomes a new leg rest. And so I know that this is carbon 4, and this is 2 because I went clockwise. 3, 5, and 6. So you got the 2 chair structures set up properly. And now what we want to do is put in our substituents. So if we think about this one more time, we noted here that, let's use that's on a wedge. So if I think about that axis again, and I tip that bond line structure down, lay it down on its face, the wedges will become upward direction, and the dash downward in some fashion. So I'm going to go to carbon 1 in chair A. I'll call this chair B. Let's focus on chair A. The wedge has got to be up at this point right here. You can see that the two bonds that connect at that carbon are pointing in the upward direction. If you think about those little arrows there, those are both going upward. So the axial has got to be straight up. And then that means the equatorial is going to be downward, okay? Wedge is up, so the axial is the up one, that's the CH3, and then the downward is a hydrogen. Okay, and I'm going to circle the non-hydrogen axial substituents. And here, I'm just going to circle that, make it easy to look at later. Let's go to the next chair. What was axial becomes equatorial, but still stays up or down accordingly. And so at carbon 1, the down, if you look at these two bonds that are connecting to make a junction at this carbon, they're both downward. So that means the axial is straight down, and then the equatorial is going to be upward. And so up stays up. So axial was up in chair A. Now the equatorial's up, and that's where the CH3 goes. And then the hydrogen is down. Okay. And so I'm not going to circle any large groups on the chair B because there's no large substituent in an axial position. You don't have to circle, but I think it helps when you analyze. So in chair A, we have a large substituent or group, axial. In chair B, we don't. And so what do I mean by large? I mean, right now, larger than hydrogen. Since hydrogen is sort of the baseline when we think about cyclohexane, when we have something larger than hydrogen, there's going to be different interactions with those other axial substituents. And so which chair is more stable? Or what's the favored conformation? I have conformation A or conformation B, and they may not be equal in energy. And so you'll want to look at the 1,3 diaxial interactions, and I'm just going to draw them in so you can see what I'm talking about, but maybe you don't need to. So I have a hydrogen there, axial, on the same face as the methyl group, and so I get here, I get 2 times the CH3 hydrogen 1,3 diaxial interactions. Over here, it's just a hydrogen interacting with other hydrogens. The equatorial is the CH3, and so the equatorial position is where the larger groups would prefer because it minimizes the 1,3 diaxial interaction. So this has no methyl hydrogen 1,3 diaxial interaction. Okay, it's all between hydrogens. And so I can say that chair B is more favored conformation for this compound, or in other words, more stable. And so you're going to learn about A values a little bit. So A values are basically delta G values. These are just energy values. The way I like to think about them is it's the penalty for placing one substituent axial versus another. So when you have an A value of 1.7, that's the A value for CH3 hydrogen interactions. So for methyl, the A value equals 1.7 kcal per mole when it interacts with those methyl hydrogen 1,3-diaxial interactions. So there are tables that give you these values. The higher the A value, the less favorable that group is in axial position. For that particular group. I'll just leave it as that. So, okay, so when you think about chair B, a hydrogen is much smaller than a methyl group. And so basically the A value there would be 0. So hydrogen, the all hydrogen case, cyclohexane is kind of baseline relative to the other values in the table. So 1.7 is higher than 0. So there's a higher penalty, a greater penalty for putting a methyl group axial versus a hydrogen axial. Okay, so chair B is the more stable conformation. All right, and I think that I'll leave it at that. If you have questions, please feel free to email me and have a good day.